Hello, welcome back everyone. Today, this is our last talk and Dixy Msapato is going to give us a talk about counting tau exceptional sequences for Nakayama algebras. Take it away, Dixy.
Thank you very much for the introduction. I'd like to start by thanking the organizers for inviting me here and allowing me to be here to speak to you today. So the title of today's talk is called Counting Tau Exceptional Sequences of Nakayama Algebras, and it's based off a paper of mine by a similar title, which is in the Algebras and Representation Theory journal, came out this year. So the outline of the talk is as follows. I just divided the talk into 4 parts. In the first part, I would talk about a brief history of exceptional sequences, mentioning where they come from and the sort of work that's been done in the area. In the second part, I would talk about tau exceptional sequences, giving basic definitions and results, which will be useful for the counting results I get later on, and the projections later on. And finally, I'll just give some closing remarks about the results I have and work going forward. So to start with, I'm just gonna give some common notation. So as usual, K is going to be an algebraically closed field. A is usually going to be a finite dimensional algebra over K. I'm going to write mod A for the category of finitely generated left A modules. And N is usually going to be reserved for the number of isomorphism classes of simple A modules. And sometime I might write delta of A to mean the same thing. And I'm also going to write int of A for the set of indecomposable modules of indecomposable A modules up to isomorphism. So first definition is as follows. Let M be a left A module. We're going to say that M is exceptional if the endomorphism ring of M is isomorphic to the underlying field K. And if there are no extensions of any degree T from M to M for T greater or equal to 1. A sequence of modules which are indecomposable M1 to MR is going to be called an exceptional sequence if each MI is exceptional, so exceptional by the definition above here. And if there is no morphisms from right to left and no extensions from right to left of any degree. So formally, xt of mj to mi is equal to 0, and hom of mj to mi is equal to 0 for t greater or equal to 1 and j greater than I. If this number r is equal to n, the number of where n is the number of simple modules up to isomorphisms, we're going to say that the sequence is a complete exceptional sequence. So exceptional sequences and exceptional modules were first introduced in the context of algebraic geometry in the study of vector bundles, mainly by the authors Bondau in 89, Goroddan 7, 88, and Goroddan 7 Rukudov in 87. The definition of an exceptional sequence and exceptional module was originally given in the context of a triangulated category. So the only difference in the triangulated case is instead of this t being a positive integer bigger than 1, t is just an integer. And the exceptional sequences were first studied in the setting of the representation theory of finite dimensional algebras later in the 90s by Pauli-Beeve in 92 and Ringel in 94. And ever since then, they've been of interest to a few authors, and they've been counted and classified, amongst other things, for example, by Seidel in 2001 and Gusso and Schiffler in 2010. More recently, exceptional sequences have received a bit more interest, in particular, receiving many generalizations. So these are the 3 main generalizations I'm aware of. The first is that of weak exceptional sequences, which was introduced in 2020 by Sen. In 2017, signed exceptional sequences were introduced by Gusso and Todorov. And in 2018, for the paper appeared only this year, some tau exception sequences were introduced by Juan and Marsh. In fact, Bethany Marsh gave quite a good talk about tau exception sequences a few weeks ago, which is maybe somewhere online. Okay, into our second part of the talk. We're just going to start by giving a few more definitions and introducing some more notation. So we're going to write curly P of A to be the subcategory of projective modules of A. Let T be a subcategory of mod A, and let M be an object in T. We say that M is X projective if the first extension of M with every object in curly T is equal to 0. And we're going to write P of curly T to just be the direct sum of indecomposable X projective modules in T up to isomorphism. Given a subcategory X, curly X, we define the perpendicular subcategories. So we have the left perpendicular subcategory, perp X, and the right perpendicular subcategory, X perp. So we define perp X to be the subcategory of modules Y such that there are no morphisms from Y to X for all objects X in curly X. And we define X perp dually. And as usual, we're going to use the letter tau to denote the Bose-Lambda write and translate. Adachi, Yama, and Wrighton introduced tau rigid modules and tilting modules. So I'm sure a lot of you are familiar with the definitions, but just to remind you anyway, a module M is called tau rigid if there are no morphisms from M to tau of M. Moreover, if M is a tau rigid module and M has n summons, n indecomposable summons up to isomorphism, then we say that M is tau tilting. Let M be a tau rigid module, and then we can define what's called the tau perpendicular category of M in mod A. This is a definition by Hasse. And the tau perpendicular category of M in mod A is just the intersection of M perp with perp of tau of M. And it's proved that it was proved by Hasse that this is in fact an extension closed subcategory of mod A. So just a couple more results which are needed. Let M be a tau rigid A module. Then we have this module called the Bungat's completion of M, which will write T of M. This is just the direct sum of the X projectives of perp tau of M. And by result of Adachi, Yama, and Wrighton, this is in fact a tau tilting module. Another result by Hasse tells us that if M is a tau rigid module, then the tau perpendicular category of M inside of mod A is in fact equivalent to a module category of this algebra here. This algebra here is just the endomorphism ring of the Bungat's completion questioned out by the ideal generated by the idempotent EM. And this is just the idempotent which corresponds to the projective module of the Bungat's completion hom TM of M. And the number of simple modules of this module category is equal to n-1. So it's just one less than the number of simples of mod A. All right, so we're now ready to define what a tau exceptional sequence is. So let R be an integer greater or equal to 1. A sequence M of indecomposable modules M1 to MR is called tau exceptional in mod A if, first of all, the MR, the end module here, is tau rigid in mod A. and the subsequence M1 to MR-1 is tau exceptional in the tau perpendicular category of MR. So this is a recursive definition. So what the second line means is that you want to check that MR-1 is tau rigid inside of this category, which is in fact just equivalent to a modular category. And then you want to check that M1 to MR-2 is a tau exceptional sequence in the tau perpendicular subcategory of MR-1 inside of this category. Moreover, if R is equal to M, we're going to say that M is a complete tau exceptional sequence. And it's these complete tau exceptional sequences which we're interested in counting. And because the definition is quite recursive by nature, we're going to see that a lot of our counting arguments are recursive in the sense that we get recursive formulas for the things we're trying to count. So this makes it fairly nice to count. Let X and Y be T sequences in mod A. So X has S objects and Y has T objects. A sequence Z with S plus T objects is going to be called an interleaving of X and Y if each Zi inside of Z comes from X or Y, and the subsequence of Z containing only objects in X is precisely just X again. And likewise, we want that the subsequence of Z containing only objects in Y is precisely just Y. So for example, if consider the sequence Z given by 5, 2, 4, 5, 6, 1, 2. This is an interleaving of X and Y because the subsequence containing only elements of X, 5, 4, 5, and 6 is again X, and likewise for Y. But something like W, which is 5, 2, 6, 4, 5, 1, 2, is not an interleaving because the subsequence of just X elements, 5, 6, 4, 5, is not the same as X. And just another point to remember, given T sequences X and Y of length S and T respectively, the number of interleaving sequences, the number of interleavings of X and Y we can get out is given by this multinomial, which is just S plus T factorial, or divided by S factorial divided by T factorial. And this would come in handy soon enough. And just one more result. So if our module categories are fairly nice, then you can sort of tell how to get the tau exceptional sequences from the related subcategories. So specifically, let A and B be finite dimensional algebras over K. Then Z is a tau exceptional sequences. Then Z is a tau exceptional sequence in mod A directs on mod B, if and only if Z is an interleaved sequence of tau exceptional sequence, says in mod A and mod B. So if you've already counted mod A and you've counted mod B, then counting mod A directs on mod B is fairly easy. And this is what we're going to use a lot. You'll see soon enough. So the title of this talk is Counting Nakayama Algebras. So I need to tell you what the algebras we're concerned with are. So the first class of algebras we're concerned with is a class of linear Nakayama algebras. And we denote them by gamma NT. And this will be the algebras which are equations of the path algebra of the linearly oriented type A quiver, questioned out by the teeth power of the arrow ideal. And we're going to look at powers between 2 and n. The other class of algebras is going to be the come from the cyclic Nakayama algebras. We're going to denote them lambda nt, and these will be coefficient algebras of the coefficient of the path algebra of the linearly oriented n cycle, quotiented out by the tth arrow ideal. And again, t is taken to be between 2 and m. So the first case we'll look at is going to be this gamma n2 case. So this is the linearly oriented case where we're questioning out by the second power of the arrow ideal. And our strategy for counting is going to be quite simple, but it takes us a long way. So our strategy is as follows. For each intercomposable m, we're going to count the number of complete tau exceptional sequences ending in m. Then we're going to sum over all of the m's to get our end result. For gamma n2, if m is indecomposable, then m is either going to be a projective at vertex I or a simple at vertex I. So there's only really two cases to consider, if you will. So lemma. So the number of complete tau exceptional sequences ending in a projective I, where I is between 1 and n, is given by the formula n minus 1 factorial, or divided by n minus I factorial, I minus 1 factorial. So this multinomial coefficient multiplied by g subscript n minus I times g subscript I minus 1, where gj is the number of complete tau exceptional sequences in mod gamma 2. So I just give a sketch of the proof to give you an idea of this counting strategy we're using, and it's going to be the same strategy for the cases we consider. So let's start by considering a complete tau exceptional sequence ending in the projective at I. Then by definition, m is a tau exceptional sequence if and only if m1 to mn minus 1 is a complete tau exceptional sequence in the tau perpendicular category of pi in mod gamma nt. So the tau perpendicular category of pi turns out to just be equivalent to the category which is given by the direct sum of mod gamma it with mod gamma n minus it. And like I said, m prime is tau exceptional sequence in gamma pi. And by an earlier proposition, m prime is going to be a tau exceptional sequence if and only if it's an interleaved sequence from mod gamma it and mod gamma nit. Because we're considering a complete tau exceptional sequence, m prime is going to be a complete tau exceptional sequence if and only if it's interleaved from two interleaved tau exceptional sequences, one coming from mod gamma it and one coming from mod gamma n minus it. So as a result, the total number of tau exceptional sequences ending at pi is given by this equation here, where this is accounting for the interleavings and this is accounting for you picking pairs of sequences from mod gamma it and mod gamma n minus it. So like I said, if m is an intercomposable module in mod gamma nt, it's going to be simple or projective. So if it's simple, the number of complete tau exceptional sequences ending in the simple is given by this multinomial coefficient multiplied by g n minus I times gi minus 1. The proof is essentially the same sort of strategy. So putting it all together, let Gn be the number of complete tau exceptional sequences in mod gamma nt. Then Gn is given by this recurrence, which we get from just summing over all the projectives, all the simples, and putting the two together. I think it should be in this one. And the initial conditions we have is that G0, G1 is equal to 1. So these are just trivial to get from calculation. We can then calculate the exponential generating function of Gn, and we get that is equal to 1 divided by 1 minus x squared divided by 2. And at this point, it's a natural question to ask whether or not this sequence we just obtained here counts other sequences of objects, combinatorial objects. And for this algebra, it turns out that the answer to that question is yes. In particular, there's a bijection between tau exceptional sequences of gamma n2 of a mod gamma n2 to the set of order set partitions of the set 1 to n with blocks of size at most 2. And we construct the bijection in the following way. So the first step is we construct a map which we call I-top, or the index of the top. And it takes an indecomposable module in mod gamma n2, and it maps to it a positive integer greater or equal to 1. So it's a fact that the tops of indecomposables in mod gamma n2 are all simple. So if an indecomposable m has top the simple at k, then I top of m is going to be equal to k. So second step, we take a tau exceptional sequence m1 to mn, and we assign to it a sequence of subsets in the following way. So the sequence of subsets is going to be called phi tilde of m, and a number t, an integer t, is going to be in the subset CR if and only if the I top of the module in position t of m is equal to r. So the index of the top of mt, if that's equal to r, then t gets put into the subset CR. So for example, consider the following complete tau exceptional sequence. Then phi tilde of m of 4, 1, 2, 1, 3, 4 is given by the subset T3, the empty set 4, 1. So we get T3 because T is going to be in C1. So this is C1 here. If and only if the top of the module in position T is equal to 1. And likewise, the top of the module in position 3 is 1. So we get T3 here. This is empty because there's no module in M, which is top 2. And you can see the rest. This is not quite as an ordered set partition. So if you forget the empty set, then you get this sequence here, which is now an ordered set partition. So it's ordered set partition 2, 3, 4, 1. Partitioning the set 1, 2, 3, 4. And this is the map which gives us a bijection between complete tau exceptional sequences of mod gamma n t and ordered set partitions of the set 1 to n with blocks of size at most 2. Now, ordered set partitions are well studied by combinatorialists, and ordered set partitions of blocks of restricted size are also studied, and they're called restricted Fabini numbers. So the restricted Fabini number, written Fn less equal to m, counts the number of ordered set partitions on the set 1 to n with blocks of size at most m. And the result by measure gives us a recurrence for restricted Fabini numbers, which says that Fn less equal to m is equal to the sum over L from 1 to M of n choose L, F n minus L less equal to M. And by the previous bijection, we're in the case of M equal to 2. So we get the following results for free, essentially. So first of all, our Gn is going to be equal to Fn less equal to 2. So we now have a new occurrence for Gn from measure, and this is quite different to the recurrence I showed you originally. I'm sure you'll agree. Oops, which is this one here. And we also get a close formula for free due to Gallet and Sangel, 2017. That completes the gamma n2 case. So we now look at the lambda n2 case. So the lambda n2 case is the case of the cyclic algebra. So the path algebra or the n cycle quotiented out by the second power of the arrow ideal. And this turns out to be quite similar or quite related to the gamma n2 case. So let Ln be the number of complete target sufficient sequences in mod lambda n2. Then, as we saw previously, the key to counting these target sufficient sequences is to calculate the tau perpendicular categories. And like in the gamma n2 case, module in lambda n2 is either projective or simple. If a projective is simple at vertex I, the tau perpendicular category is equivalent to mod gamma n minus 1, 2. And if it's a simple module, then you're equivalent to mod gamma n minus 2, 2 with mod gamma 1, 2. We already know the number of target sufficient sequences for mod gamma n2. So as a result of that, we get that Ln is given by n times Gn minus 1. So this is from considering the target sufficient sequences ending in projectives, and plus n times n minus 1 Gn minus 2. This is from considering the target sufficient sequences ending as simples. And we sort of get for free this exponential generating function for Ln and this closed formula for Ln. The third case we consider is the lambda n to the n case. So this is again a cyclic Nakayama algebra. So this is the quotient of the path algebra of the n cycle, quotiented out by the nth power of the arrow ideal. We're going to let Hn be the number of complete target sufficient sequences in mod lambda n to the n. And by a similar counting strategy, we can derive the following recurrence relation for Hn. So Hn is going to be equal to n multiplied by the sum over I from I to 1 to n of n minus 1 choose I minus I, multiplied by I times I to the minus 2 times Hn minus I, with the initial condition that H0 is equal to 1. We can then calculate the exponential generating function of Hn, and we get that is equal to 1 divided by 1 plus W of minus X. And W is this function called Lambert's W function. And it's a function that actually appears in very many places in maths in general. So one of the places you might see it is in combinatorics. If you're ever concerned about enumerating trees, Lambert's function usually appears in the form of the tree function, which is, and I think the tree function T of X is defined to be W of 1 minus X. And it also appears in areas of applied maths. So it's used, interestingly, I thought, in the calculation of wave heights. So it's quite surprising to see it in this context of representation theory of finite dimensional algebras. But unfortunately for us, this exponential generating function is known. And it turns out this is the exponential generating function for the sequence n to the n. So we conclude that h to the n has a closed formula n to the n, which again counts many combinatorial sets. And if one is familiar with weak exceptional sequences, they might remember or notice that the full weak exceptional sequences in mod lambda n to the n are also counted by sequence n to the n. So just to tell you what weak exceptional sequences are, the sequence of indecomposable modules M1 to MR is called weak exceptional if the endomorphism ring of each Mi is isomorphic to K, the underlying field, and there's zero extensions. There's no extensions of degree 1 from M1, Mi to Mi. The second condition is that there's no morphisms from right to left, and there's no extensions of degree 1 from right to left. So this is a bit like the weak exceptionist. This is a bit like exceptional sequences, except that we can allow the higher extensions to be non-zero. And we say that M is a full weak exceptional sequence if M has maximal size. So I guess a property of weak exceptional sequences is that unlike complete exceptional sequences, the size of the sequence is not bounded above by the number of simples. So we noticed that weak exceptional sequences are counted by the same formula as type exceptional sequences. So you might ask whether or not this is a coincidence. And it turns out actually that the complete type exceptional sequences in mod lambda n to the n are precisely four weak exceptional sequences in mod lambda n to the n. And this is generally not true for an arbitrary algebra. So I think if you consider mod lambda n to the t, my counting result is different from the one Sang gets when they count weak exceptional sequences. And you might also ask me about projections to other combinatorial sets, because the sequence n to the n, like I said, counts many things. It counts, one of the things it does count is the following sequences, the following set of sequences. So let Bn be the set of n by n matrices with entries from 0 or 1, such that each row has exactly 1, 1. And then I think that the following map is a projection. I currently haven't proved it. And if anyone can see why it's a projection, I'd be interested to know why. So the projection works in the following way. You take a tau exceptional sequence M from M1 to Mn, and then this goes to the matrix A, which is equal to Aij, and Aij is going to be equal to 1 if and only if the index at the top in the ith position is equal to j. Just to point out, this psi here is not the same as this psi. Check this projection, or check this map rather, on small examples, and it seems to hold, so I'm pretty convinced, but proving it is quite a different task. But the last case we consider is the case of gamma n to the n minus 1. This is a linear Nakayama algebra. So it's the algebra which is the quotient algebra of the path algebra of linear linearly oriented type A enquiver with the quantitated out by the n-1th power of the arrow ideal. And so far, strategy has been quite good. But this is the first time where a strategy still sort of works, but it becomes less effective, let's say. So from a strategy, we can derive following recurrence relation for Km. And it's pretty long, with the initial condition that K1 is equal to 1. And if you try to then calculate the exponential generating function, that's also quite tricky. But the best thing, or the next best thing I could do is, from trying to do that, is to derive this first order linearity for h of x. Yeah, theoretically, this should be easy to integrate, but it's not, because you're having this this Lambert's function w is again appearing in our terms, and generally integrating things involving Lambert's function is not, it's not easy. Okay. So the title of the talk was Counting Tau Exception Sequences for Nakayama Algebras. And obviously there's more classes of Nakayama algebras than the ones we have counted. And I'd like to justify why I haven't done that. Essentially, it's because our strategy fails, and it fails for a very good reason. So in all of our counting arguments, the first thing we sort of did was calculate. Well, we took an incomposable modulo M, and we wanted to count the number of Tau exception sequences ending in that modulo M. And so the first thing we have to do is then calculate the Tau perpendicular category of M. And in all of our cases, J of M was just a direct sum of modular categories of algebras of the form lambda m prime t prime, or the form gamma m prime t. In the other cases, particularly when t is greater than 3, n is greater than t plus 1, there exists some modulo M such that the Tau perpendicular category of M, it's not a direct sum of modular categories of algebras on the form lambda n prime to the t or gamma n prime to the t. In fact, I'm not even sure if the algebras you do get are Nakayama algebras. And the proof is just really by counterexample. So considering the simple odd one, if you calculate the Tau perpendicular category of the simple odd one, you get that it's not of the desired form. So that's the failure of the strategy in the cyclic case, and it's the same case, same story in the linear case. If t is greater than or equal to 3 and n is greater than or equal to t, then the Tau perpendicular category of M, again, it's not a direct sum of modular categories of algebras in the form lambda m prime to t prime or gamma m prime t prime. And this is a proof by counterexample again, by considering the case when m is equal to s1. But there's other modules as well which satisfy, which work as a counterexample to these two propositions. And that concludes my talk. Thank you very much for listening, and I hope you enjoyed it.
Thank you for this nice talk. I will first ask people in the room if they have questions. Brittany has a question for me.
Thank you. Can you hear me, Dixie?
I can hear you.
Okay, great. I had a question about the bijection phi, I think it was, to ordered set partitions.
Yeah. Yes.
So I was thinking about how your proof goes. Do you have an explicit inverse for phi, or is the proof done in a different way?
Yeah, it's not an explicit inverse by showing that the map phi is injective. It would be nice to get an inverse, but I feel like I'm somehow losing information. For example, on this step, I have to forget about the empty set, but the empty set is actually telling me a lot of information about what the sequence might look like, because it tells me where the tops are, and I think there's a statement which says that which tells you the order. I think essentially a projective with certain top always has to be after the simple with the same top. So for example, you can never have 1 before 1, 2. So there's a lot of information you can like guess about the sequence by knowing by knowing where the empty set lies. But as soon as I forget that, it's harder then to like guess what the original exceptional sequence was. So yeah, so fortunately I don't have an inverse.
Oh, I see. And it's difficult to say what phi bar hits, which sequences arise in the image of phi bar.
Yeah.
Okay, thank you. That's interesting.
Thank you, Bethany. I have a question. So for these collection of complete tau exceptional sequences, can you form a poset? Can you put an order on them?
Right. I guess in general, I don't know. And I suppose Bethany would be a better place to answer that. But I guess for me, for this case, you could, based off the bijection. But I think, yeah, it's posets. I don't know. Yeah, I think for exceptional sequences, you can do things like that because there's a mutation thing you can do on exceptional sequences. But I'm not sure if you can mutate. Well, I don't know if it's known if you can mutate complete tau sequences in a similar way to get a poset.
Okay. Are there any questions from the Zoom audience?
I have one.
Yes, go ahead, Sibylle.
Okay, excellent. Okay, so I was wondering, in the case of the, was it lambda 2n and gamma 2n, this Hasso category, the tau perpendicular category, it decomposes into a direct sum. Can you say a little bit why? I mean, is there some intuitive reason why this is happening?
Okay. Yeah. So I guess it goes back to this proposition. So the tau perpendicular category you sort of get by considering the endomorphism algebra of the Bong-gas completion, and to question that by EM, I think you basically end up removing a vertex in the corresponding quiver. And a lot of the times the quiver gets split into two type A quivers, which also turn out to be the right thing.
See. Okay.
So yeah, the cases where it doesn't work, when you do remove the vertex, you get a quiver, which is not unlike the original ones you started with.
I see. Okay, super. Thanks. That's very helpful. And then I had another question, if that's okay. So when you consider the cyclic Nakayama algebra, so if you have n vertices, you consider relations of length at most n. Is that right? So you don't have any overlapping relations.
Yeah, I didn't consider anything of length. Yeah.
Okay. Okay. Thank you.
Any other questions from the room or from the Zoom audience? Nick has a question.
Hi. I was just wondering, in these cases where these tau perpendicular categories don't decompose like you want them to, just which other sorts of algebras arise? Is it essentially just like different orientations of type A, or do we get other stuff as well?
I think we get other stuff as well. If I vaguely remember, one of the things I did get was sort of like an end cycle with a tail. So, and something like that.
Like a tadpole.
Yeah, tadpole type.
Thanks.
Yeah.
Any other questions? Not in the room. What about in the Zoom? I don't see any questions, so let's thanks Dixy again. I would like to thank all the speakers of the INI seminar series. Yeah, this has been a very wonderful conference, and thank you very much, everyone, to make it happen, especially the organizers. Hope that in the future we will have more of these events and we will get together. Thank you, everyone, joining. Hope to see you in the next event.
And once more, thank you, organizers.
Thank
This
you.
was really, really nice of you to organize all of this. Thank you very much.